Hello, everyone. Thank you for joining today's demo webinar. My name is Dave Triano. I'm Senior Sales Engineer with LucidWorks. And today we're going to dig into how to build a recommendations engine with LucidWorks Fusion. So a little bit about myself. As I said, Senior Sales Engineer. I'm based in the Boston area. I've been with LucidWorks about a year and a half. And I got started in search and recommendations about 10 years ago, working on search and recommendations around movies and music and TV shows. And here I am 10 years later talking about the same fun stuff. So excited to talk to you guys today about recommendations. For today, we'll plan for about a half hour consisting of some prep discussion around recommendations. The meat of the webinar here will be a live demo showcasing a couple of ways to build recommenders with Fusion. And then finally, I'll leave some time at the end for Q&A. I'll also say you have a question box. If you have questions throughout, you can also feel free to enter them as we go here, and I'll try my best to keep an eye out and answer as we go as well. Okay, so since everyone on here is pretty familiar with LucidWorks and Fusion already, I'm going to keep the overview of the company and product itself pretty short and sweet. We have been in the search and recommendation space for over a decade at this point, with our product Fusion going on about 6 years or so. So we operate in a few solution spaces. E-commerce is a large part of the customer base that we serve, and these customers are leveraging Fusion to drive more relevant and personalized search and discovery, often in their online stores. So some example companies, Lowe's, Bed Bath & Beyond, more recently Lululemon and CDW are using us. Okay, so this is a very high-level overview of how Fusion sits between your data and application. And when we talk about data, it really consists of a few different flavors of data. So there's what we call human-generated data. This can be your web pages. It can be products in your catalog. There's application-generated data, data that sits in applications like transaction history and order history. And then there's system-generated data, or what we typically call signals, which are sort of the implicit user behaviors that we're collecting. So as users are using your website, they're issuing queries, they're clicking on products, they're adding those to carts. These are all user behaviors that we're collecting. Okay. Now, Fusion itself then leverages machine learning at ingest time and offline to do things like build recommenders, and then we apply those at query time for a personalized. Okay, so a little bit about the kinds of use cases that we can address with the recommenders that we're going to build today. So if you are, do online shopping, you're probably familiar with most of these. So product detail page recommendations. I have an example here where if you're viewing, let's say, the product detail page for an Instant Pot, along the bottom, you might see a little note that says, hey, customers who view this product also tend to view these other products. And then you can see some other pressure cookers and multi-cookers there. Similarly, homepage recommendations. So as users come back to your website and you know a little bit about them, you know some past products that they've looked at, you can just sort of surface recommendations for them. Like, hey, you might be interested in checking this out, but they're not necessarily on the product detail page. Within a cart, so this is similar to the PDP, but it's a little bit more cross-sell related. So if someone adds an Instant Pot to their cart, you probably don't want to surface a recommendation within the cart for other pressure cookers, but you may want to surface recommendations for something like the hard-boiled egg cooker insert for the Instant Pot, right? Like something that a user can that will add into their cart. Okay. Aside from those sort of product-related recommendations, we can also talk just more generically about things like queries. So similar queries are actually going to be powered by the same exact techniques that we use for, say, item similarities, like in the first case. So this example on the bottom right, this is from a home product store, where if I issue a query for pot, I can see some similar queries show up along the bottom, say for Cuisinart cookware or Emerald cookware as well. Even though those queries don't mention pot as well, there's sort of this similarity based on what other users tend to search for when they also search for pot. Okay? And then aside from that, we can talk about recommendations even more generically, just on content in general, right? Like this doesn't have to be about products necessarily. This could be about articles, news articles, or really any documents as well. Okay, so in the recommender space, it's a rather large space, and there are kind of two families of recommenders. So the one that we're going to look at today, we call collaborative recommenders, also known as collaborative filtering. And these are the recommenders that are built on user behavior, sort of crowdsourced recommenders. The other family that we won't spend as much time on is content-based recommenders, where it's not based on the crowd or user interactions. It's more just based on the content itself or metadata about particular items. So in the collaborative space, these are based on signals, the queries and clicks and cart ads, et cetera. And it's basically a two-step process. So we start with our raw signals. We then, from there, generate aggregated signals, what we call a user item matrix, also known as a user item preference matrix. And it looks a little bit like this, where your rows will be your users, and your items might be your columns. And within each cell is just a number. And we're going to talk about a couple of ways that we can come up with those numbers and how important it is to come up with, how important those numbers factor into the different kinds of recommenders that you can build. The other thing that I would mention here is that a user doesn't necessarily have to be an individual. It could be a behavior. So one example that we see is for item similarities. Query strings actually do a really good job at coming up with item similarities if you enter that as a user. The theory there behind that is that as users you have a lot of users who search for jeans, let's say, and blue jeans, and men's jeans and women's jeans and bootcut-like jeans, and then take associated actions on those queries. Those queries are similar enough. They sort of have the same kind of intent and similar but diverse enough follow-on actions that they can actually do a really good job coming up with item similarities. So in our example, we're actually going to look at behavior-based collaborative recommender once we get into the demo. I'm going to skip a bit of the math, the matrix math behind recommenders, and if we have time or there are questions, I can jump back to this. And this is a little bit more graphical view of what this actually looks like in production. So moving from left to right, we just talked about the sort of two-step process where we go from raw signals, run an out-of-the-box aggregation job to come up with those aggregated signals, a user item preference matrix. We can then run multiple jobs to come up with our recommendations, our pre-computed recommendations. So that ALS job, ALS there is for alternating least squares, is essentially the algorithm under the hood that goes from a user item preference matrix to those pre-computed recommendations. So this is all happening offline. And then with those pre-computed recommendations, we can then, for example, do product detail page recommendations where, as a user is browsing around your site onto a particular product page, you have that product ID. You send that as part of the request, and Fusion can immediately respond with a list of recommended products that you then display. So in terms of the time that's taken, like the reason why the left side of this is offline, is that those aggregation jobs, those can be sort of minutes if you have a lot of data, and depending on the size of your cluster, possibly hours. And then ALS itself is also sort of a minutes to hours kind of runtime. So these are not things that you can run online. You can't compute these things as users are browsing around because obviously we want the right side of this online to be millisecond response times. Okay, final slide before we jump into the demo. We're going to dig into what I'll call proximity-based recommendations. I made up that term, but the idea here is that as users are coming to your site and clicking around, there's sort of a sequence to what they do, and the distance that that a user that's between particular item views is sort of important. We can kind of factor that into how we build our model. So in this diagram here, the circles A, B, C, and D represent items, perhaps products in a catalog, and then the arrows, each color represents an individual user's path. So I can see that the orange user goes from item A to B and then to C. Same with the green user. And then the red and yellow users go from items A to D. Okay, so there's sort of this natural thought here that comes out that it's like, well, A and C are sort of related. There's some relationship between those, but it's not quite as strong as A to D, right? Like people aren't directly going from A to C. So we'll use this. The reason why this kind of factors in and why we're going to show it here is that people often shop online or browse online very similar to how they shop in a brick and mortar store. At least I do. So when it comes to Christmas time, I'll do my kid shopping and look at all the games and books, etc. And then I'll move on to my parents and buy the gifts that I get from my parents, candles and whatnot. So most users will actually do this as they're browsing news or Wikipedia, for example. So by taking this into account, we can actually get some interesting nuance come out in our recommendations. Okay, and with that, I will jump into a live demo at this point. So I have two browser tabs open here. We have the Fusion admin console that I'm going to log into. And then I also built an application here to go and view the recommendations that we come up with. So as you can see, we're actually going to be dealing in Wikipedia. There are a couple of reasons why I picked Wikipedia. One is that the content itself is obviously freely available. And the other is that Wikimedia actually publishes Clickstream data as well. So if I jump into my collections manager, you can see the content that I've indexed here. So there's that human-generated content in this Wikipedia collection. So we have about 10 million documents within here. This is actually English Wikipedia. And I'm not actually indexing content itself. You can see there are only a few pages that matter, or sorry, a few fields that matter here. So one is this page ID that if you browse Wikipedia should look familiar, where it's pretty human-friendly, but you'll see underscores for spaces and things like that. So we're indexing that. We have the contributor username. We have the friendlier title indexed. We also have a URL where this actually links off into Wikipedia. And that's about it. We're not actually going to build an application that does search on Wikipedia content. We're just interested in collaborative filtering recommendations. So the key that I want you to tuck away for now is this page ID field that has the Wikipedia ID that also shows up down here in the URL. Okay, the other piece of data that we generated is that system-generated data. So that Clickstream data that Wikimedia makes available to us. So just to show you an example of what one of those documents looks like, there are really only a couple important fields in here. So there's a source field. In this case, Raymond Coppa is an example. And you can think of this as just the starting point where a particular user is. And then there's where they go. So they may have gotten to the source organically, just gone to the page. They may have Googled and clicked a link. But then we do know that from this Raymond Coppa page, they clicked on the Coppa Trophy Wikipedia page. So this is a type link. So these are actually, of the 31 million or so signals that we've indexed, these 20 million link signals are the ones that actually matter and that we're going to build our recommender on. So if you think back to the diagram, that two-step process that I showed where we go from raw signals to aggregated signals or user item preference matrix, there's a built-in job that you can go and look at called, in this case, it's user item preferences aggregation. And if you look in here, this is the out-of-the-box model that we use to come up with that user item preference matrix. So you can weight certain event types differently. So clicks are a little bit less important than cart ads, which are a little bit less important than purchases. And you can see within here the underlying SQL that's used to actually generate that matrix. And we do some time decay so that recent signals factor in a little bit more strongly. We apply that weighted sum. And then ultimately, we're just grouping by document ID and user ID, which happen to be the row and column of our user item preference matrix. So this is really that step one that's out of the box. In our case, because we're having a little bit of fun with that Wikimedia Clickstream data, I actually generated a custom created a custom aggregation here. And the only interesting thing that I did here is take the count that Wikimedia provides us, and I'm just applying a log function to that. The reason for this is to kind of dampen the effect of large difference. As counts get big, the difference between counts tend to matter less. So this is a common thing to do in information retrieval in general. The difference between 1 and 100 clicks is much more significant than the difference between 1,000,000 clicks and 1,100,000. So that's all we're doing there. There's a second one here that we can also look at that I call closure aggregation. Closure just because this is doing a little bit more in graph theory called transitive closure, which is actually doing some self-joining here to take steps. So we have our raw signals, and then we also take a step right here where I join those signals to the clickstream itself, and I'm joining on the destination of one being the source of another. So I'm kind of chaining these together in order to get that proximity. Okay, so those are the two example training set generation jobs that we're going to look at. Now, given those training sets, there are two ALS jobs, alternating least squares jobs, that we can look at now. And the first one that we'll look at corresponds to the first clickstream aggregation job, so I called it Rex baseline. And if we dig in there, there are a few important things to note. So one is the training collection. This was the output collection of that first job. And I'm telling it where to put item similarities. So a new collection that I call article Rex. And for this case, we don't actually have user IDs in that data set, so we're not going to do any items for user recommendations, just item to item. And aside from that, there are a few other things to note. I'm going to say, give me 10 item similarities. So for every article in Wikipedia, give me 10 item similarities as long as there's enough data. And the other important part of this is essentially a descriptor of what that matrix looks like. So because both of our aggregation jobs are outputting to the same collection, we have a filter query here where this job is only running for that first aggregation job. And I'm specifying the user ID, and this is a behavior-based user ID, where it's really just where a user is. So this is kind of similar to that query as user ID idea that we discussed before. And from there, the item ID, where a user goes, sort of their click from there, is going to be the destination. And we have our weight field. The next couple sections dictate how that matrix math works, how big those matrix factors should be, and how factors that influence how overfit, that control overfitting. And then finally, there's an item metadata setting. This is actually the first part where the human-generated content actually matters. We could just go and generate recommendations from one ID to another. But here, we're going to actually tack on some metadata. In this case, just the title or the URL that comes from our primary Wikipedia collection. And if you remember what the ID was in that collection, it was just the page ID _s. So we reference that here. And that's it for our job. We run that job. These jobs took about 20, 25 minutes on the machine that they're running on. There's one other job here, so a similar job, same exact thing for Rex transitive, for that transitive closure. That takes a little bit of an extra step in the training set. And the only difference there is that the filter query references that second aggregation. So other than that, these are exactly the same. And the result of running this, we can look at results in Fusion. So if we jump over to the article Rex collection and jump into the query Workbench, I can display a couple of fields. So they are called item ID and other item ID. And this is basically showing us the 2.6 million recommendations that we've come up with. So the title here is our items, and then for each of these, the subtitle is a recommended item. So, for example, for the Wikipedia page for Basketball Association of America, we would recommend Allen Houston show up. So Allen Houston, remember him from the New York Knicks as a basketball player. Okay, so given that, we have a little friendlier UI over here that was built with App Studio. So if I log in to here, this is a very simple application thrown together in a couple hours. So really just meant for quick prototyping and to let us see some of the results here for Wikipedia recommendations. So for this, I'm going to have a little fun. I recently watched all of the Marvel Comic Universe movies, so that's going to be our theme for today. So we could, for example, search for Thanos. If you're familiar, Thanos is the bad guy in the Marvel Comic Universe, or one of the many, but a really bad guy. And see here at the top that I'm actually pulling an image and title and the Wikipedia summary itself. This is, if you recall, we're not actually indexing this data. This is actually pulled in through the App Studio connector to Wikipedia. So just sort of a little plug for App Studio, even though this webinar is not about App Studio. And you can see down here the different flavors of recommendations. So just for demo purposes, we're showing our baseline recs. And you can see that the baseline recs here sort of makes sense. They're very close to Thanos, right? Thanos is the bad guy who collected all the Infinity Gems, and when he did, he was able to snap his fingers and do really bad things. Jim Starlin is the comic artist who designed Thanos and wrote some comics around Thanos. If you look at the transitive recs, we get a little bit more dangerous in terms of the recs that we pick. So, for example, Squadron Supreme is a group, a superhero group, kind of similar to the Avengers, but there's not really anything about Thanos in here. And then similarly, if you go to the Thanos webpage and even search for Squadron Supreme, it's not even in here. But you can sort of imagine why Squadron Supreme would show up as a recommendation, being kind of similar to the Avengers. Let's see, some other examples here. Let's take Iron Man as another one. Okay, I'm just going to paste that in. Sorry, bear with me. Okay, there we go. So for Iron Man, you can see some of the baseline recommendations. Again, those very closely related to Iron Man, like Pepper Potts, Iron Man's love interest. The transitive recs get a little bit more dangerous. So Wolverine shows up. Both Marvel Comic Universe, or both Marvel characters, but actually don't have a ton of overlap. And if we went and looked at their Wikipedia pages, you would not see mention. So they just get a little bit more dangerous as we go. One final one that I'll show you, this one I found to be pretty funny. So if you know Ant-Man or seen Ant-Man, so this is the, I'll say the more kind of ridiculous movie. You know, Paul Rudd is the star in Ant-Man. It's not quite a Captain America, not quite an Iron Man, a little less serious. He's just funny. And if you look at some of the transitive recs, this one I thought was very funny. So this four-bush man showing up. So he and Ant-Man have nothing in common other than both being Marvel characters. But he's sort of this ridiculous fictional employee of a parody company called Marvel Comics. And if you go and look up Four-Bush Man, even on Google, you can kind of see he's a little bit similar to Ant-Man in terms of having pretty ridiculous skills and looking kind of ridiculous. He has a pot on his head. He's a little bit overweight. So again, sort of one of those Marvel characters that's just there to sort of make you laugh. So at least my theory is that that shows up as a recommendation for Ant-Man because of that. And with that, we have about 5 minutes left here. So I'm going to jump out of the live demo. And please go ahead and enter questions in the box, and we'll do a little bit of Q&A for the remainder of the time here. And bear with me 1 second because I closed my window by accident. I'm going to rejoin and right now and look at the questions that you all are pasting in. Okay. So I can see a few questions. So first one here, why not build a recommender like this just based on counts, meaning that the most popular destinations for a given source are recommended? And that is a great question. Let me hang on a second. Let me share my screen one more time. Okay, so that is a great question. So that's actually a valid way to go and build a recommender. There are a couple weaknesses of that. So one is that that approach is highly subject to what we call popularity bias, which means that sort of the most popular hops that people take, those are going to be the only hops that show up as recommendations. You're not really going to get much nuance showing up with those. It's also what I'll call the rich get richer problem. So as you surface those recommendations, those are the hops that people take, and as a result, those recommendations are only more and more likely to surface as recommendations. Alternating least squares and similar collaborative filtering algorithms do a much better job in terms of handling popularity bias and also for handling, on the other end, sort of less trafficked items. They can do a really good job of coming up with good recs. Compared to just a strict count-based approach. So that was a good question. Let's see, another one here. How do you handle recommendations for new users or products? That's a good one because as we built our recommender here, this was built on Clickstream Data. So what happens for, what do you do in the case of in our case, let's say a new item that shows up, a new movie that comes out next month and a page starts on Wikipedia is written. What do we do for recommendations there? And for that case, right, we can't really rely on just strict collaborative filtering. For that case, for the case of new products or new articles, we probably go more toward a content-based approach. And overall, you might put in what we call a hybrid approach, where for things like new items, it can take that sort of more content-based approach, but for existing items, you take the collaborative approach. There are other sort of mixed approaches as well, where you could use collaborative filtering to come up with recommendations based on attributes. So in the case of, let's say, clothing, for example, you could come up with just recommendations for men's jeans, like just that category, men's jeans, and use collaborative filtering to come up with all the top recommendations for men's jeans in aggregate. And that way, when a new article of clothing that's men's jeans comes out, and there's no Clickstream data for it, you could query that kind of hybrid model to go and show some recommended products. So that's one approach for it. Let's see, another question here. How do you verify transitive connections? So in this case, this is just done based on, with the Wikimedia data set, we're given those source and destination IDs. So the data itself is actually very clean. In the case of an actual site where you're doing, you're actually tracking users and you have cookies, you'll likely want to base that based on the same session, let's say. You could also do users as well. And then the other thing to consider also in reality is sort of different omni-channel, right? So if you have the same user visiting your site on their home laptop and then their work PC and then their phone, and you can stitch all of those together, that's one way to handle that. Let's see. Another question here. How do you measure the quality of one recommender versus another? So that's a great question, and the answer there is experiments, because often you won't know. You don't know. You come up with a couple recommenders. You don't necessarily know which one is better than the other. And if we jump back into Fusion. And I can show you very quickly how that would look. So you can set up an experiment, bear with me right here, over in a query profile. So a query profile is just an endpoint. You can see there are two endpoints here, item rex baseline, and then transitive. And these I put these in place to basically power those two lists of recommendations. Of course, in a real store, you wouldn't have multiple lists of recommendations, right? That would just confuse users. They're the same kind of thing, just different algorithms under the hood. So in our case, what we would do to experiment and actually test one recommendation model versus another is we would have just one query profile, and we would enable experimentation and create a new experiment. And within there, we could have a couple of versions. So let's say we have our baseline, and this will call into the baseline query pipeline. And as we add another variant, that'll send, this is 50-50, a 50-50 experiment. You could also change that. But we will have, let's say, the second kind, and the only difference here is that this will call the transitive query pipeline. And then finally, because it's an experiment, we need a way to measure it. So for that, we can add a measure, and we have some built-in metrics here, as well as just custom ways to go and measure. But you can, for example, specify click-through rate, run your experiment, and then over time, over a day or a week, et cetera, kind of see the winner based on click-through rate. So that's how that would work. We're about 5 minutes over now, so if there are any other questions, here's a good one. How many days worth of signals data need to be persisted for the ALS recommendation model? So that's a great question. How much data do you need to actually run this? And the answer here is that there are a few different kinds of data. So you have your catalog size, a user base size, and then just the number of interactions. So the catalog itself, as long as it's not trivially small, like some small Shopify store that only has 5 products, you're okay. So you can have a catalog with a few thousand products, and that's totally fine. User base, similarly, doesn't have to be that big. As long as it's big enough to get what I'll call similar but diverse enough behaviors to go and generate sort of quality-looking recommendations, then you're okay. And then most importantly here, though, is the number of interactions. And again, because the diversity sort of matters here, typically my rule of thumb is you're okay in single-digit millions for total interactions. So in this demo, we had more than enough interactions. We had about 20, 30 million signals. For most of our engagements, even just quick engagements to build custom demos for customers, as long as we're in the single-digit millions, we get very good recommendations, both for users as well as item-item similarities. That's a great question. And with that, we've gone about 6 minutes over. I think we can end the session. Again, thank you all for joining. If you would like, you can feel free to reach out with me. I'll put my email back up on the screen here. Feel free to email me and follow up, and I'd love to talk to you. Thanks again. Have a nice day.